question about 107?
Sorry, she's rude. Say again.
Could I ask a question about 107 on 9.5?
Okay.
Just that, so I think it was the problem about 18% of high schoolers smoking.
Yeah, from the CDC.
Right.
Okay.
And so the claim, though, is from the local, right? The local school that they want evidence that it's lower than 0.18, right?
That's right.
Okay. So then, so I put that as the alternative hypothesis.
Well,
since that has the less than.
Good. Yes. Okay.
Okay. And the null hypothesis would be the opposite, right? P is greater than or equal to.
Yeah.
Point.
Yeah. Okay.
Okay. But then when we do the sample population percentage, 0.546, so I guess I basically set it up as a left one-sided test since the alternative hypothesis is the less than, right? But then 0.546 is way out there on the right. When I calculate the Z-score, it's like 11.66.
Yes.
So it's nowhere near the rejection region.
That's right.
Okay.
So this is a funny problem. To me, this is a problem. We wouldn't even do the test. So for example, if I'm like, I think it's less than 18%. What was your p-hat?
P-hat was 0.546, the 82 out of 150.
So what do you think about the claim less than 18? Is there any reason to do a test?
It's not even on the same side of the mean.
Exactly.
So
to be honest, I wouldn't even do the test. I mean, that's an obvious one. So in order to show evidence, not only does the sample have to be less than 18, it's got to be like a lot less than 18 or some predetermined amount less than 18. If it's greater than 18, screw the test. It's like, no, dude, you have no chance. Right?
Okay. Okay, because this problem was like driving me up a wall for a while, kind of like, why are we even doing the test? But okay, cool, thank you.
Yeah, so I mean, to be honest, it would have been nice to see somebody go, I didn't see why to do this shit, and I would have been like, I agree with you. But not on every problem. And there was somebody who's like, every problem, they're like, no, that's not no. I told everybody, even if you think you shouldn't be able to do it, you still do it. And you voice your opposition, but you still do it. You want the practice. Could we go over the end of 4.2 homework? 4.2?
I'm going back through corrections right now.
Oh, I see. Okay.
Yeah.
Yeah, that's a office hours question or something. Or when we do the final exam review on Wednesday. Yeah. All right, guys. Anything else? Yes.
Can I ask a question about chapter 12?
Oh, that's the only one that I'm not taking questions. Okay. Number 12. Sorry, I'm being an asshole. Okay. Number what now? 72?
12.5, number 72H. So I just filled in the 6 for X.
Good.
But it's asking, does it give an accurate estimate?
Good.
And the reason why I'm thinking it might not is because 6 stories is so below the rest of that data.
Good.
And that 100, would it really be 100 feet?
Good. That's exactly it. When you create a correlation, the line of best fit will only work to predict for things within the data you were given. Right? Because, for example, if you follow a fish and you record if you record the length of a fish for the first 10 days of its life, and then you just kind of extend that line, you'll be like, oh my God, in 2 months, this fish will be larger than New York. And it's like, no, dude, calm down. It only works within the data you had you got. Yeah, that's exactly right. Go ahead.
Okay. And then for I, if you're just looking to add an extra story, you're just looking to add 11.76 feet.
Yeah, that's the
you already have your stuff.
That is the most algebra related problem that I think that happens in the whole class. That is a slope question. Yes. I like it.
Okay. Thank you.
When's the last day, guys? When's the last day to turn in corrections?
The day of the final?
Yes, so Thursday. before the final happens, by the way, not Thursday midnight or something. Because what's the point? Why am I letting you do corrections? What do I hope happens?
We actually learn this stuff.
Yeah, and so you can show me what you've learned on the final. So don't do shit after the final because I'm not going to take it. I have definitely not graded many homework corrections. That is for damn sure, because my focus was on grading new homework and grading corrected quizzes and midterms, because those are the things that are going to affect your grade the most. Somebody with me? If there's any homework that you have burning questions about, you can send me an email and say, could you please look over my corrections? Because there's a really good chance I'm not going to be able to look at them at all. So you could be like, well, what does that mean? I'll give you the benefit of the doubt. If I don't have the time to look at it, I'll give you the benefit of the doubt. You guys understand what I'm saying?
Yeah.
No, that's not the benefit of the doubt. Does not mean you won't get credit. That's the opposite of the benefit of the doubt.
Yeah.
Right. So the benefit of the doubt means any doubt that I have, I will give you the benefit of it. So meaning I'll assume you did them right. Does that make sense? Now, obviously, if I get a bunch of corrections now from somebody right before the final, I might take a look at those.
Damn it.
Yeah, exactly. Oh, look at that. I just got to turn it in. He's going to give me all credit. No.
All right.
Oh, this is okay. All right. All right, guys. Anything else? Does that make sense? Everybody okay? Everybody understand what's happening on Wednesday? Does anybody know?
Our quizzes due, I'm guessing?
No.
Practice?
Review midterm.
Yeah, we're getting ready for the final. So Wednesday is all review for the final. You understand? So did anybody notice I put the practice final up there? I put the solutions videos. I opened those up. That's Jeff from 2 or 3 semesters ago. So that's before I really knew how to do much. So good luck with it. Technological. Anything else, guys, before we jump into new stuff?
Can you go over real quick how to tell the difference or how to determine if it's a one-tailed and then if it's left or right?
Yeah, it really is. You look at your HA, right? And if it says less than, the tail is on the left. Less than, so it's going to be down. If this is greater than, up. Tail's on the right. If it says not equal to, it's 2 tails. I really want that, yeah, because and again, the way we set up hypothesis tests is that the HA is what I can show evidence for. Let me ask you this. Can a sample ever show evidence that the mean equals something? If I take a sample, go ahead. Sorry.
No, you only have a certain amount of confidence or certainty.
Sure, yeah, so there's always going to be some wobble, right? So I can't use a sample to show evidence of equality. And doesn't the HO have an equal sign in it by definition? That's why we set it up that way. So what sets up where and how many tails is HA? That's the one I can show evidence for. If it says less than, I got to get a sample that's quite a bit less than, unusually less than. That's why the tail would be down. If it says greater than, other way. If it says not equal to, either way would work. That's why it's a 2-tail test. Okay, maybe?
Yes, thank you.
Sure. Really, so much in this class makes sense. Physically, it makes sense. It just makes sense. And I know that you guys are like, for you maybe, math boy, but I desperately want you to realize there's a reason we did it the way we did. It actually does make sense, and not just to weird math people. Anything else? Okay. Let me see. Damn. So let me catch up with what we did last time. I don't remember now. All right. So we have definitely finished Maybe, do you guys want to do another example, I would think, of chapter 12?
I have a quick question about one of the homeworks that we just turned in.
Okay.
The very last one for 9.5. I wish I was looking at it, but I didn't know whether or not to do like less than or greater than or equal to, or just straight up like equal or not equal, because I think in the question it said kind of like two things that could have been either.
All right. So do you remember which number it was?
It was the very last one, so 115, right?
115?
Yeah.
The one about the mean family size?
Maybe.
Oh, okay. All right, guys. So here's the thing. Listen, guys. If somebody came along and they said, no, I think the mean is more than 50. What must, all right, stay with me. I really was. If somebody came along and they said, I think the mean is more than 50, who are they talking to, and what does the person think that they're talking to? Does that make sense? If somebody came along and you just came into the room and you heard this one guy say to this other guy, no, I think the mean is more than 50. What does the other guy think?
So then we would use the claim being is the class's mean family size greater than?
Yes. Yes.
Okay, I see.
Yeah, the first sentence just sets up what the claim relates to. Does that make sense? They have to tell me what the average is. If the claim is it's greater than the average, they better freaking tell me what the average is, right? The national average. Does that make sense? So the very first sentence says, am I showing this? Yes. According to the New York Times Almanac, the mean family size in the US is 3.18. That's not a claim. That is, you can argue it's a claim of some kind, but it's just what's in the almanac. So that's what we take. It's given to us. So now the claim makes sense. It's greater than the national average. Oh, so it's greater than 3.18. Thank you for telling me what the average was. Are you guys understanding? I understand the problem, because you look at it, you're like, is mu equals. Yeah, I know. No, you know, shit, the actual claim was greater than. Exactly. Good. All right. So let me ask this again. Do you guys want to do another example from chapter 12? Or how do you guys feel about chapter 12 correlation stuff? Have we really even done an example besides these here?
It would be good to do a review.
All right, let's do real quick. Hold on. Let me see where I've got stuff at here. I think Donde está? I don't know. Oh, Scheisse. Hold on, guys. Hold on. What do you do all morning, Jeff? Why don't you get ready for class? Be quiet. All right, let me see if I got this worksheet. I got another example from chapter 12, if I could find it real quick. Chi-square. No, not chi-square, was it? Correlation. Here we go. No, that's not the right one. Shit. How you guys been? You doing all right? Hold on, everybody.
Statistically?
Sure.
Not so well. Physically, actually, my back's finally getting better. The physical therapy's working. So
Oh, sweet.
yeah.
Physical therapy can be a lot, you know.
It's a lot of time, but it's better than taking pills.
All right. I thought I had another correlation problem, but apparently not. All right, so let's make one up. Okay. Oh yeah, let me do this. How am I gonna do this? I don't know, Jeff. Oh, it's taking too long. Oh, I know. Why don't we just do the one off the practice final? I like it. Anybody have a problem with that? Let's see. Has anyone ever been to Bronx Pizza, by the way? Anyway. All right. It's down in Hillcrest, by the way. And if you go there, don't yell at me if you start to gain weight, because it's really, really yummy. It's really yummy. And I ate too much of it. So this is a correlation problem. I know the very first part of number 5 is about making a confidence interval. So we're not going to do that right now. All right, so let's focus on BCD. So if you want to play along with me, go ahead and put this data into L1 and L2. Let me zoom in a little bit. Is that better? This data right here, right? Oh, let me do it in my virtual calculator. Okay. Oh, good. It's still working. Thank God. Everybody understands what's happening right now, right? Y'all should be doing something. Let's see how far you can get. Can you get the entire scatter plot, line of best fit? Can you get all that showing up on your screen? And if not, I'm going to do it with you here in a minute. That's weird. Oh, weird. Everybody doing okay out there? Are you? Does anyone still need this up there?
No.
Billy is the group spokesperson. Let me show you. Let me show you.
Generally the slowest.
So here's the data, right? Where do I go from here to? Well, let's graph the scatter plot first. How do I get the scatter plot to show up? If you're using the same calculator as before, one thing I would say is to go to y equals and take this out. That's no longer good. Are you with me? Whatever's in y equals is no longer good unless you've already put the right line in there or whatever. If I just hit graph, I get this.
Do you do Zoom?
Good. Zoom.
9?
Zoom 9. By the way, real quick, I told you guys about my eyeball, right? In case anybody, I can't remember what side, in case anybody worries about why it's all bloody. Gross. Did I tell you about my eyeball? Oh, I don't know. You probably don't want to
You
hear.
didn't do it in this class. You did it last class.
That's right. Because this, I get a shot in my eye every 7 weeks. I know. I'm sorry. Should have had a warning. I'm sorry. It's interesting. Anyway, I lost like a lot of sight in this eye suddenly. And January 2019. I was up in Temecula with some friends, went to had some drinks, went somewhere to look at some books because we're all geeks, and I suddenly couldn't see out of that eye. Anyway, so yeah, this is the last week, so you're not going to see this anymore. So just so you know, it's why it's bloody. Sorry. Hopefully you're not eating something right now. Did you guys get this?
Yes.
Everybody else? To get the scatter plot, you hit zoom. And then for me, it's the 9th option, zoom stat. Okay. So that's kind of nice. It means you're on the right track. Is everybody good? Everybody good? Now, how do I get the line of best fit and the correlation coefficient, the R value? R. How do I do that? Anybody? How do I get the line of best fit and the
And if
R?
you go to stat and go over to calc, and it's the number 4.
Yep. You can tell there's the line, right? MX plus B, just an A there, just to be different. L1 is my X's, L2 is my Y's. You can do this if you want to.
Wait, we do stat, calc, and then
Stat, calc, and then it kind of gives itself away. There's the line, see it?
number 4.
And then L1 is your X's, L2 is your Y's. I'm going to skip this for now. So there we go. And if you're using a different calculator or you weren't here when we did this, is anybody not getting these?
Yeah, I'm not getting those.
All right. So here's what you're going to have to do. And anybody else who's not getting those, you only have to do this once. You hit second, 0. This is a catalog of everything the calculator can do. Then you hit, are you with me so far?
Mm-hmm.
Then you hit this button right there to get to the D section. Bam. So it should start with day of week. Very interesting. Scroll down to diagnostic on. Then hit enter, enter. So far, so good?
I think so. Yeah.
Set this. All right, good. So now you're giving me access to your bank account. I'm joking. Now, if you go to stat, calc, number 4, and you do it again, you should get those.
So stat,
Calc,
calc,
number
four.
4. Yeah. And then L1, L2, calculate.
Yeah, we're good.
Cool. Can somebody tell me what's your initial reaction to seeing this R value here?
It's very strong.
Yeah, it's really close to -1. Now, I forgot to put this on the practice test, but on the actual final, I'm going to tell you what R has to be greater than. And if I remember correctly, and I don't, so I'm not even going to try to pretend. I think R had to be greater than 0.5 something for this, because this is kind of a small sample. Would you agree with me? Yeah. The sample's not that big. It's not crazy small. It's not like 3 things, but it's not that big. So R had to be greater than something. I think on the answer key, I say, if you watch the solutions video, I tell you what it was. But this, even just looking at this and the fact that it's not like only 4 data points, that's pretty close to strong, right? That's pretty close to -1, which is perfect. And of course, we saw this picture looks really good, right? It's obviously not perfect, but it's pretty good. So how do I get my line to show up if I forgot the shortcut way to do it?
Go to y equals.
Yep, go to y equals, and I'm going to put in there. Let me see if I can remember this. Let's see if you can do it, Jeff. -2.87x plus 218 point, I forgot.
5.8.
Thank you. Right, be careful you hit the negative button, right? Negative button down here. And then we get to see my awful color scheme. Actually, now, again, I know why I think of ice cream, because isn't that there's a color in the Baskin Robbins logo? Right? There you
Yeah.
go. Yeah. That's funny. And does that do what you, does everybody get that show up? Okay, on their calculator? Yes. And does it do what it's supposed to?
Can you do that again?
Yeah. So you go to y equals. And by the way, so before we go here, you would know this stuff here, right? So you can keep track. What's the slope? Negative 2.87 roughly, right? And what's the y-intercept? 218.58.
Then what do we hit to go back to the graph?
Hold on. Then you go to y equals and you put all that information in, right? And your X button is right here. There's your X button. And then you just hit graph. Okay.
Wait, your X button, damn it. Oh, graph. Ah, it's actually spelled out for you.
It's crazy. All right, so let's come back to the sheet. Where are you? Oh man, hold on. Okay. So the questions I ask. So you would just put down the line of best fit. Remember, part A is a confidence interval. We're not doing that right now. Line of best fit, the R value. I would tell you R has to be less than whatever or something. But again, you already basically told me, what would an R value of negative 0.907, what does it tell you? Is it strong or weak?
Strong.
Strong. What kind of correlation? Negative, positive. Yeah. So
Negative.
Strong negative correlation. That's what this question. Well, actually, I'll tell you this. I would ask you to interpret R, and that would be strong negative correlation. Then I'll ask you, what does it tell us about the line of best fit? You could say one of two things. Does somebody know what to say there? What does the R tell us about the line of best fit? Since R is really close to -1.
That the miles you live away from Bronx Pizza affects the weight in pounds.
Well, we don't know the cause and effect. We have no idea which one affects which, right? It could just be that. Yeah.
Fit between distance and weight.
But that's less about the line of best fit and more about the relationship between the variables. I want to know, what does it tell us about the line of best fit? Were the data points really close to the line? Relatively?
Yes.
Yes. And what would make them further away? If the points were further away, what would the R value be?
Lower.
Yeah, closer to 0, right? So R of negative 0.907 tells me that the data points are close to the line, right? That's one way you can answer that question. One way to answer this question is data points close to the line. Another way to answer this question is we would trust the line to make predictions. I think I've said that before, right? The closer R is to 1 or -1, the more I trust it to make accurate predictions. So how would I do this? And this is interesting. Why am I technically not allowed to do this?
Because it's outside of the
Good.
interval, or I don't know.
Yeah, exactly. It starts at 1.5, right? The data points start at 1.5 miles, and I want half a mile. But oh well, I'm just telling you to do it. So we're just going to go, all right, Jeff, we'll do it. So how would I do it?
And put it into X.
Yeah, half a mile. X is the miles. So I would throw 0.5 into my equation, my line of best fit, and out would pop the answer. Right. How you guys feeling out there? You guys okay? Okay.
Can we just run through that equation that we're popping x into?
Yeah, what was the equation that we put in there? Was remember this much?
Y equals negative 2.87, that equation?
Yeah. So now I know the miles is half a mile. Miles was list 1, that's x's. So I would put 0.5 in for x right there. And that would be the prediction, right? Of course, this prediction, I don't know how it would do because it's outside of our data, but oh well. People still try to do that. They still try to put stuff in outside of the data, especially stock market stuff. Look at the line, let's put some money. Oh shit. It's economics 101, kids. Yay, no. Okay. Maybe. And of course, I mean, if you don't know what I've written here, it's okay, because all the answers are in the solutions video that are up there now.
On the test, would you want us to answer this answer is irrelevant because it's outside of our...
No, I would give you one that's within the data points.
So their weight would be 217.145 pounds.
Yeah, that's what you got when you put it in. That sounds about right. Yeah.
Okay, I did something right.
Woo! By the way, this was me. That was me when I lived in Hillcrest. I blame it all on Bronx Pizza. Which button do you press to get this? Did I answer that? Is that from a long time ago? I don't know. Do you still have that question out there? Right, that was the Zoom 9. I think I answered that question. I can't remember now. Okay. So that's chapter 12, right? So now we're going to talk about chapter 11. We're going to file bankruptcy. It's funny, Jeff. All right, be quiet. All right. So what I want you to realize is what we've done so far is we've talked about, for example, with correlation, how many variables can we compare at once? How many variables do we normally compare with correlation stuff? Two, right? We want to see if there's a relationship between two variables. When I talk about weight, when I talk about grade on a test, when I talk about whatever, is there something else beyond the number of beers you drank last night that might affect the grade on the test? Is there any other variable, or is that the only thing?
Yes.
Yes, of course there are other variables, right? So one thing we're not going to have time to do, but I just want to kind of let you know, is that there are ways to analyze more than one variable at a time, right? More than two variables at a time. So there are ways to analyze the effects, but the relationship between more than two variables at a time, because normally there's definitely more than two variables that could be affecting a situation, right? So what we're going to do in chapter 11 is we're going to introduce this new distribution, and I really, okay, let me just jump into it. So let me ask you this: what distribution do we use when we're talking about means and stuff? We're talking about means. In fact, I just had it up here, right? What distribution do we have to know? What kind of distribution does it have to be?
Normal.
I love it. What governs the shape of a normal distribution? What governs the shape? So like if here I got a normal distribution, here he is, right? And then I got this guy over here. Here he is. They're both normal curves. Why are they differently shaped? What one thing would tell you, so let's say the means are the same. What is the thing that is making them shaped differently?
The Z or the T-score?
No.
Standard deviation.
Standard deviation, exactly. Sorry, let me close this. Sorry, all right. So what if, so I could use normal curves. Even this is freaking me out. I could use normal curves to do a test between means. I could do a normal distribution to do a test between percentages. Are you guys with me? We did that all in chapter 9. Okay. So I'm trying to do multiple things at once and it's not working really well. Here, there we go, it's better. I want you guys to see my beautiful normal curves. Mute somebody, there we go. All right. So sigma determines the shape, which determines how far you've got to go. So for example, if it looked like this, I'd have to maybe just go to here and find a sample. But if it looked like this, I might have to go way out there. All right, I don't know if you guys are with me at all. Are you guys semi with me a little bit? No, that's not a thumb up. That's your pencil. All right. Now, so I could do a test about the hypothesis test about a mean. I could do a hypothesis test about a percentage, right? I could create a confidence interval for means. I can create a confidence interval for percentages. I can do a lot of shit, all that beautiful shit, because we have this beautiful theoretical idea of a normal curve, and sigma is the shape of it, or even maybe S would be the shape of it, right? Determine the shape. Is everybody, okay, I'll stop asking. Now, what if I wanted to, for example, create a confidence interval or do a hypothesis test about a standard deviation? What if somebody said, I claim that the standard deviation of grades in this class is more than 15, right? Do you guys understand that I could not use this because this is how, maybe I can do that. This is how little means are distributed, right? And this tells me the shape of how they're distributed. Yes, or it could be how p hats are distributed, right? Right, could be how p hats are distributed. Yes, maybe. Okay, now. So, anything that I want to do that involves creating a confidence interval or testing a claim about a standard deviation, I obviously, this is not the right distribution. This is not how standard deviations are distributed. So what, oh shit, I should have done this. So for this picture, what formula kind of goes along? There's an official formula for the curve, but what formula do I find out how far something is from the mean? What formula do I use? Give me one example. There's many. I love you guys. You're not sure what to say.
Is it mean? Oh wait, no.
So what formula would I use to figure out how far something is away from the mean? What tells me that? What gives me distance in statistics?
Z or T-score.
Beautiful. So one example would be this. Somebody give me another example. What's another formula for Z? I'll start. Go ahead.
Sample mean?
Sure. Sample mean minus the mean of the means divided by this new standard deviation, 11. What about this one? This is the one, the newest one, right? Remember that guy? I love it. I have no idea what it's like for you guys. You're like, just get to your freaking point, Jeff. Just get a point and get to it. All right. I'm getting there. This is such a nice, okay. So I know this picture works for means and for percentages. I know that this idea works for this shape. Okay, maybe. So, and I know that this or this, they're both kind of related, right? They control the shape of this thing. So if my claim was about this guy, what the shit distribution does this guy live in, right? I don't know if you guys are with me now, because who lives in there? X bars live in there, or P hats live in there. Do you understand what I mean when I say live in there? No? You're all like, I haven't understood a word since maybe day 2. I'm sorry. All right. So again, remember when I was saying we take a sample and we plot the sample mean. We take another sample, we plot the sample mean. We take another sample. Okay, I get it, Jeff. So I can do the same thing with take a sample and plot the p hat. Take a sample and plot the p hat. And make this shape. Sigmas don't live in there. Sigma tells me the shape. All right, I'll stop. So there is a different shape. There's a different distribution that the standard deviations themselves follow. So if I took a bunch of samples and found S for each one, and in much the same vein as recall, let me see. I can make a z-score for any, let me make it like this. Any sample mean I get, I can make a z-score out of it and see where it falls in the picture, right? So much like this, for sigma, we can make, so the formula that's sort of like a z-score for the standard deviations is this formula. This is looking a little weird. Right, you guys? But what's n-1? Do you guys remember what's that called?
Degrees of freedom.
Degrees of freedom. I love it. And of course, that's the standard deviation for a sample, right? That's the standard deviation for a population, right? I really want to see. I haven't told you what the hell this is yet because this is going to freak you out. But hold on. Do you see how there's a population standard deviation and a sample standard deviation? And they're compared. In this case, they're divided. What happens in a z-score formula? There's the population mean, there's the sample mean, and they're compared, in this case, with subtraction. All right, so it's not like, I'm not saying that the formulas are the same. I'm definitely not saying that. I'm saying you can see parallels between them.
That's n-1, comma, n-.
Not comma, times, right? n-1 times s squared divided by sigma squared. So for just to remind you guys, up here, if I knew the mean was 10, the population mean was 10, and I know my sample mean is 7, and I know my standard deviation, my new standard deviation is 2, couldn't you figure out the z-score and tell where it lands in the chart? Yes? Okay. That is what this does for standard deviations. If you take a sample and you get an S, you can compare it to the population standard deviation and see where it would fall in the picture. Now, I haven't drawn the picture yet. I'm just trying to build my way up there. So this we call a z-score, right? That's what we call a z-score, and it kind of falls in the picture. This one we call, get ready, we call it chi-square. Become a Q. It's just the name of it. Notice it's spelled C-H-I, and it's not chai, it's not chai, it's chi. And it's not Dragon Ball Z chi, I'm sorry, it's spelled wrong for that, right? I got some reaction there. Okay. Some of you guys are like, if I knew this guy watched Dragon Ball, we'll take it somebody else. All right. So if I do this, let's say I take samples of size 20, it doesn't really matter, and I do this formula and I plot the results, I'm gonna get this kind of picture. Is that a normal curve? Now I really want you, so this is the new, not new, this is the picture for how standard deviations are spread out. Can somebody tell me, why is there a hard wall here? I never drew that. Remember, normal curves look like that? Because that could go less than 0 and so forth. Do you see how this is a hard wall here? It doesn't go past there? Because what's the smallest that a standard deviation can be? Can it be negative?
No.
Sorry, so somebody say it. What's the smallest it could be?
0.
0. So the smallest this thing can be is 0. And then it goes up to infinity theoretically. Oh yeah. Is this a normal curve?
No.
Hell no. Can somebody tell me it's skewed what?
Right.
Skewed right. I affectionately call it the Jabba the Hutt distribution. But again, sorry, it's too many references, Jeff, in one class. I'll stop. It looks a little bit like, whoa. Sorry. Oh, most of you guys are like, I don't know what this shit this guy's talking. So the kind of problems we're gonna do. So the funny thing is, this to me is the traditional formula to start with. Stay with me. So this is a lot like this formula. This one and this one are very, very similar in what they do. If I calculate this, it'll tell me where the thing is. The same way if I calculate this, it'll tell me where the thing is. The one huge difference is that, let's say 2 differences. Is this symmetric? Is this symmetric? Is it a reflection of itself? No, this is not symmetric. Obviously not. It's got a big ass tail in that way and it stops dead there. Not symmetric, right? Can it go negative? No. So what sucks is here I had like 1.96, negative 1.96. Remember that? Remember those days? You thought that was bad and now you're like, that was okay actually. We can't have that shit anymore. We can't because this stops at 0. So maybe I would have something like 4.29 and 15.97. That would be possible values of this. All right, there's too many chats happening. Let me see if I can catch up. Which button? Oh no. So for chi-squared problem, the data we have to know is n, s, and population. Yeah. So if I had a problem that was sort of like this kind of problem was in the past, where I could get a z-score and figure out the probability, I could actually use this formula to do very much the same thing. So I could use this formula if I had to test a claim about a standard deviation. Somebody's like, I think the standard deviation is more than 15. Then I could do this formula to figure out the Z star kind of thing. Where did my sample get? I don't know if that makes any sense. So this formula is not the same as this, but this formula accomplishes the same thing this does. So let's now this is interesting enough on its own. Let me introduce to you the first thing we're going to do, and it's called, get ready for this, it's called a goodness of fit test. A goodness of fit test. This is the name of it. It's not my thing that I made up. Okay. I want to remind you guys, was this the only formula that we had listed up here earlier for Z? Were there more than this? Wasn't there this one, for example? Or if you did the bonus section, wasn't there this one? I'm bored already. I'm blah, blah, that one, right? So they all represent a z-score. They're all representing a z-score. They all use that picture, right? If it's normal, but they are obviously different ideas inside of them. Yes, yes, yes. I mean, this is something we've sort of inherently understood. We're using the same picture. If they're normal, we're using the same picture, but the formula can be drastically different. It actually means the same thing. Same thing for chi-square. That is not the only formula for chi-square. So the other formula we're going to create, and I think we're going to do that first. Then we'll take a break. Then we'll look at the chart, and then we'll do an example problem, and then we'll see what time it is. Yeah, let's get ready. All right. So let me just write down the name of this and see if you guys can guess what this tries to do. Goodness of fit test. This is not a physical fitness test. This is when I have data, and I want to see. So let me see. How can I say this? Oh, I got it. That's kind of boring. I don't care, Jeff. Good point. So what if I roll a die? Let me say I roll a die. What do you got, Jeff? Just put something down. There. See, yeah. 180 times. There we go, buddy. Normal die. Well, let me say this. A 6-sided die. We actually don't know if it's normal or not yet. So if you find a die, is it possible somebody has weighted it so that it comes up a certain number more often? Of course it is, right? Some of you guys, maybe you've done that before. I want to know about it. Or maybe I do, in case you want to bet me something. So if I roll a die 180 times, what are the possible outcomes?
1 through 6.
Yeah, 1, 2, 3, 4, 5, 6. So there are 6 categories of thing that can happen. It's a little weird way to say it, but there are 6 categories. Right? When I roll it, I could get 1s or 2s or 3s. Or how many would you expect in each category? How many of each would you expect to show up? Do you expect
30.
Go ahead. Yeah, 30. Why'd you get 30?
180 divided by 6.
Beautiful, because if you just found a die, would there be any reason to expect any of the numbers to show up more or less often? No. You're going to start with, all right, assuming this is a good die, I expect 30 of each. Is everybody with me? Or with us? Or with it? Or however else you would say it? Okay. Like it. So far, that's pretty easy. What kind of distribution is this? By the way, what kind of distribution is this?
Normal.
No, definitely not normal.
Uniform.
Uniform, kick ass. This is an example of a uniform distribution of stuff. Uniformly distributed the 180 times amongst the 6 categories. That's why you divide it. Now, what if we actually roll it? So we have some observed values. Oh my God, Jeff. Yeah, the word observed needed another letter. I'm gonna run out of room. I am. All right, let's hold on. I should have warned you guys too. You're gonna need some more room for this. All right, there we go. So this is expected. I'm sorry. Yeah, this is expected. You can do it, buddy. There you go. And then observed. So let's say that we observe. So we actually roll the damn thing now, right? And let's say we get, what do you got, Jeff? I don't know. I don't know. Let's say 40 of those. Let's say we get 28 of those. Let's see, 25 of those. We get 20 of those. 20, 40, 60, 70, 13. Okay. So therefore, I got 67. So, oh, that sucks. I didn't want to do that. Make this one. No, it doesn't matter, Jeff. It really doesn't. And then we get 33 and 34. I think that does it, right? 60, 100, 160.
Yeah.
180. Okay, good. So I'm trying to make this equal 180, of course, because we roll a die 180 times. Now, let me ask you right now. Did our observations match with our expectations? No.
No.
Is it enough evidence to say that the die performs differently than expected in general?
No.
Is it impossible to have a normal die that hasn't been messed with, right? Almost said F with, jeez. That hasn't been messed with, and you get 181s. Is that impossible?
It's not
No.
possible, but highly unlikely.
Highly unlikely, but it is not impossible, right? But if it happens to you, number one, you got to worry why you're rolling a die 180 times. Maybe reevaluate life choices. But secondly, that would be freaky. That would be freaky. Not impossible, but holy shit. So this feels a lot. No, don't worry. I'm going to say something. I am not going to make this into a hypothesis test. Did you hear me? We are not going to do a full hypothesis test. Good Lord, Jeff. We're not going to do a full hypothesis test. There it is. But doesn't this feel like it? Why doesn't this prove that the die has been tampered with? Why doesn't this prove it? Look, they're different. Why doesn't that prove it?
It's not different enough.
I don't know.
There's not enough rolls. There needs to be a lot more rolls.
Okay. Yeah, there would have to be a lot more rolls. So this is just a sample of rolls, isn't it? This is a relatively small sample. Consider any die that's ever existed. How many times do you think they've been rolled? 100, more than 180. All right. So it's just like in the hypothesis test. I don't stop when I get something different than the mean and go, I just found evidence. No, because like somebody else just said, it's got to be different enough. The problem is, this is not a normal distribution. I can't. So let's keep going. What's the first step, do you think, considering it's all about how different the die did? What do you think I'm going to do first to start getting a feel for that?
Observe minus expected.
Bullshit. And let's go ahead and do this. This should feel very familiar. We are going to have to square it. We might as well just go ahead and square it. Do you guys remember when we did standard deviation? Like a million years ago or 5 weeks ago or one of those two. We squared it because some was negative, some was positive, and that made everything suck. Okay. So does that make sense? If I'm doing a test about how well the observations fit with expectations, then shouldn't I subtract the damn two of them at some point? That only makes sense. So here I get negative 10, 10, but it's squared anyway. Who gives a shit? 100. Are you guys understanding? Somebody see where that 100 came from? Let me know if not. Maybe some of you guys are somewhere else watching Dragon Ball Z because I said it. If so, tell me later which episode. And then 2 squared, and then 5 squared, and then 10 squared, and then 3 squared, and then 4 squared. Good Lord, Jeff. I'm not really that bad. Whoa, okay. Well, okay. Now, I really want this next step to make sense. If I expect 30, let's see, how do I want to say this? If I expect $30, but I get $40, that's pretty good, right? If I expect $1, but I get $11, what do you think about that situation? Isn't that better? Or if I go the other way, I expect $1 million and I get $1,010,000. Am I gonna go 10 extra dollars? Holy shit! Is that? I already did that with $1 million. And somebody's like, "Oh, here's an extra 10." I'm like, "Don't even give that shit to me." Right? Or no? Are you guys at all with me? So we've seen this kind of thing happen very many times in this class before. I want to know relatively how big is this difference. So I want to take what we just did and divide it by the expected. Relative to what I expected. Just like in the case, I thought I was going to get $30 and I got 40 instead. Okay, wow, cool. Right? But if I thought I was going to get 3 million and I got 3,010,000 instead, whatever, right? If I thought I was going to get 1 penny and I got $10.01, damn, yay! You know, so that same $10 means different thing based on what my expectation was. Are you guys understanding the idea? Okay, good. Maybe you are. Okay. So now we need some help. 100 divided by 30 is 3.3333, right? You guys gonna help me? 4 divided by 30? I don't know.
1.333.
Oh, of course I knew that. Silly Jeff. Math is for kids. And then 25 divided by 30, give me a second. 0.8333.
Yes.
Dude. All right. And then, oh yeah, 100 divided by 30, we already know. And then 9 divided by 30 is 3/10 is 0.3. I'm really sorry that this is so crappy here. I got a handout, believe it or not, so we'll do another. Right, 9 divided by 30 is 0.3. And then 16 divided by 30 is something. I don't know. Should I know that? Yes. Let me see. Hold on. It's 0.5333. Is that right? 16 divided by 30? 0.5333?
Yes.
Okay. So here's what's kind of cool. This variable here, let me get here. The sum of these, that variable actually follows this new picture. So just like the z-score has multiple formulas that come back to a z-score, and I wrote some of the p-hats and the x-bars and whatever, chi-squared, this distribution, this picture, comes from, is related to several different formulas for chi-square. So another chi-square formula is the sum, the sum of the observed minus expected squared divided by expected. Okay. So what do I get when I sum these up? Can somebody help me out? What do you get when you sum those up? So that is
8.467.
Oh, thank God. Thank you. Does that agree? Anybody else trying to do that? Looks about right. 47 8 point. Well, is that true? 47 8. It's gotta be 9 point something.
I got 9.656.
Yeah. Okay. Yeah. It might be my fault because they all get really tight. Really, the 0.533 at the end. Sorry, 9 point what? Sorry, 9 point what? Did I freeze? I'm always scared.
I deleted it. Like 9.5.
Somebody's help me out. Of course. I made a mistake right there. You might have said this way earlier. This is Jeff being really stupid. 4 divided by 30 can't be bigger than 1, Jeff. So maybe that other number was correct.
Okay, I was worried because I did it in the table and I had it calculate it for me.
Yeah, please correct me when I do that kind of silly thing. I'm still a human. I'll still do that. So probably the first number was right then, maybe. Is that
Yeah,
what you think?
8.467.
All right, so everybody else, I'm sorry. That was my mistake. 4 divided by 30 is 0.133, and I had 1.33. Jeff, you should just retire. All right, so what we're gonna do, I kind of want to give you guys a break. This is sort of like, this is like Z star, because that's from our sample, correct? I still need to see, listen. If the observations were exactly the same as the expected, what would this be? What would it equal? If these were the same as these, what would be here? You could do it. I know you can. If these were the same, this is 30, 30, 30, 30, 30, 30, what would we get at the end? No work to do. Anybody? And if this was the same as this, what do I get here? If these are the same,
0.
zeros, right? So this would be 0. So if my sample was exactly the same as my expectation, it would end up right there at 0. Yes? So what we're about to do when we come back from break, don't go away yet, is we still have to set up where the rejection region is. How far do we have to get? So then we can see, was this far enough away? But I think this is not a horrible place for a break. Let's take a break because the chart's going to take a little while to talk about. While we do that, I can actually unlock the chart for you. That'd probably be a good idea. Hello, students.
Check.
Yes. Are you just checking in?
Here.
Okay.
I had.
Oh, I'm sorry, dude. I muted you. I'm an asshole. Just want to make it official. All right. So if you go into Canvas now, you will see under, oh yeah, good. Avocado and ice cream. That's interesting. Let me show you where this is. Should not be a surprise if you go to, oh, did I show you this or was this during the break? Everybody, your grades have been updated down here, right? Apparently, if you look at it in a phone app, these might not be in the right order. So you might have to look through and find them. But do you remember these 3 grades? I made them after the midterm. I finally updated them again now, including the last 2 quizzes we took and all the corrections that I graded. So that should pretty much be. And early next week, Jeff, that's too late. As soon as I get all the quizzes from today graded, and they're due tomorrow at midnight, by the way, I will update these grades and I will add in there what grade you need on the final to pass, what grade you need on the final to make a B, that kind of stuff. You guys all with me? So then you have kind of a target in mind. Okay. But the thing we're working on right now, if you could please go to module unit 11. Somebody's chatting at me. Oh, I just said it. Today's quiz is due tomorrow at midnight. Okay. Here's the chi-square chart. Let's start with this. So then we can finish this problem on the board. All right, can you guys all get that bad boy? What is this? This is new. Alternative formats. What? All right, go away. All right. So I repeat to yourself, this is the last chart. This is the last chart, all right? No more charts after this one, at least not for my class. All right, so let's figure out how the hell to read this. So what I want to do, I want to try to capture what we got on the board here. We got 8.467. Let me draw a picture up here. right, let me give myself, there we go, that's good. All right. So we got chi-square of 8.467, right? Yes. That's kind of like our Z star. That's sort of like our Z star, right? So we need to do the rejection region. And I told you I wasn't going to make this a full. I'm not going to have to do the 5 steps. You're just going to have to do the 2 most important steps. What's far enough away and how far away did we get? So we already know how far away we got. We got this far away from 0. I really want this to make nothing but sense. 0 would mean that our sample perfectly lined up with our observations, with our expectations, sorry. So our observations perfectly lined up with our expectations. Are you guys with me? That's what I was talking about before. Everybody with me? So 0 or close to 0 means that's not evidence that they're different. So it wouldn't be evidence that this dye was tampered with if we were somewhere in here. So I have to be further than that. I have to say, where does unusual start? Unusual would be far away from 0. So what if I was, so I didn't say what alpha was, so we have to assume it's 0.05, right? So the next thing I need to know is, how do I get the degrees of freedom? Degrees of freedom. All right. You guys are so gonna love this. All right, new chart and a new degree of freedom formula. What? This one's nice. This one's not evil. How many categories did we say we had up here for this problem?
6.
6, because there were 6 sides of the die. So there are 6 categories. So the degrees of freedom, because math people can't spell, it's K minus 1, where K is the number of categories. I mean, they tried, they got close. It's the right sound. So what's the degrees of freedom for this, of course?
Five.
Okay, cool, thank you. So alpha is 0.05. And notice it says to the right, this, oh boy, you're gonna love all of this. So the Z-score chart tells us the area to the left, right? This one's all about, this is the area to the right. So there's 0.05 in here. That's what would make it really unusual for a sample to show up out there, correct? It's only a 5% chance of happening. So if I go to degrees of freedom of 5, and I go over to alpha 0.05, that's what I get. That is where unusual starts. Did we make it far enough away to show evidence that the dye has been tampered with, that it's unusual? How far did we make it? Anybody?
To 11.071.
No. Where did I get that from? That came from the chart. How far did our sample make it?
To 8.4.
Yeah. So this is just like the rejection region number, right? And this is the one that we calculated from our observations. This is from our sample. You guys with me? I know how much you hate hypothesis tests. I understand that. I totally do. This takes the best parts of that, the ones that I hope make the most sense. Here's how far we had to make it, and this is how far we made it. So we have failed to show evidence that this dye has been tampered. We can't say that this dye has been tampered with. Does that mean it wasn't tampered with?
No.
No, it just means we haven't shown evidence. Right? So we find this dye not guilty of being tampered with. Could it have been tampered with? Yeah. Have people been found guilty that actually did it? Oh, hell yes. The other way around too, which is worse, which is why we probably should stop killing people. But no, anyway, that's a whole different thing. I don't want to go down that road right now. Let's not talk about it. All right. So that's all you got to show me. You don't have to do a complete hypothesis test. So let's do another example that's a little less messy. that you can follow along better. Has everybody got what they want from this?
Sorry, real quickly, degrees of freedom is K minus 1.
What does the K stand for?
Categories.
Categories. I love it. The number of categories. So that's why this one was 6 minus 1. That was the degrees of freedom is 5. I love it. All right. So I'm going to stop sharing. You guys ready? I'm going to stop sharing this.
I have a question.
Yes.
Or I just need confirmation. You said that 0 would mean that our observation lines up perfectly with the expectations?
Because the only way I can get 0 for chi-square is if these are exactly the same. So these are all zeros.
Okay. All right.
Like, and that would obviously, now that would not be evidence that the die has not been tampered with. It just isn't enough evidence to say it has been tampered with. How many people does that sentence I just said drive crazy? I don't know. Like, what the hell did this guy just say? So be really careful. Just because a sample doesn't make it far enough away, and if it's exactly 0, it's like, that's got to be evidence it's a good die. Nope, it's not evidence. It's just definitely nowhere near enough evidence that it's been tampered with, that the die murdered the other die. It's not enough evidence. Okay. I'm going to stop sharing and see if somebody yells at me.
Wait.
Okay.
Almost there.
If you go to Canvas,
Okay.
I think I unlocked, you go to, I unlocked the other thing, didn't I? Let's see. Here, yeah. Now what's funny is this is what I had in mind. See how it says correlation practice? I had a whole worksheet with another correlation problem, but you could try that if you want to, and maybe I'll put the answer key up. But we're gonna focus on this. So I have a problem that I did. So this is M&Ms, right? Anybody else, when you ate M&Ms when you were a little kid, did you separate the colors? I always did. Yeah, I always did. Towards what end? I have no idea, but I just did. So this is a completely worked out problem. There are 6 categories. So again, the degrees of freedom is 5. Alpha is 0.05. That's why we got, see the 11.071, just like we got. So this is the rejection region up here. Look how pretty this is. Yeah, you can definitely tell Jeff did not draw this shit. What is happening out there? I gotta mute somebody. Oh, there we go. Okay. And then this, now we're trying to test to see if they're uniformly distributed. And of course, I have 42 M&Ms. So then why did I put 7 next to everybody? Why is that my expected amount?
You divide by the number of categories.
Yeah, if it's uniformly distributed, they each get the same amount. So I just divide the total by how many categories. So they each get the same amount. I like it. Is this necessarily going to always be a whole number?
No.
No, I've just been kind of nice on my examples. This could be whatever the hell I get when I divide, right? Okay. So again, so this is a fully worked out problem. You can kind of look at it as an example for later. So this one we're going to do together because it's the other type. So one type is uniform distribution test. Does it follow a uniform? Is it uniformly distributed? Do they all show up in equal amounts? That's what that test does. The other kind of goodness of fit is they give me percentages like this. So this is blood cholesterol levels for the general population. Do this. They follow this distribution. And I'm curious, we go to a secluded area. Let's say we go to a little island, right? And we see cholesterol levels there of people. And we want to know, do these people follow the same distribution? They seem healthier, right? Was anybody around back when olive oil was like people were just guzzling olive oil because studies came out showing that people that lived in the Mediterranean were healthier. And Americans, being as smart as we are, we said, they use olive oil. Let's drink olive oil. And I was, what? No, they also walk a lot more than we do. They also eat less processed shit than we do. But no, it's the olive oil. It's got to be the olive oil. I pour it on my Big Mac. Everything's going to be great. Anyway, so that's back. That's a while back. I can't remember when that happened. And now it's like red apple vinegar or something. I don't know. Is it right? All right. Whatever the hell. It doesn't work, kids. Just stop it.
Apple cider vinegar.
Red apple cider vinegar? Okay. All right. I think I'm thinking about some hard cider. I want some hard cider. All right. So let's see, how the hell am I going to do this shit? So up here, it was uniformly distributed is what I was testing it for. So that's simple. I just divide them evenly. Here, let's do the first thing. Let's do the easy thing first. The observations have to be easy. I have to just tell you what those are. Can you guys take a minute and just fill in the observed values? So read through this and see if you can fill in the observed values. Damn it, I'm all out. So you guys see that? So like 132 below 130. So that's a 132 there. 219 between 130 and 200. So that's 219. 101. 101. And the rest. Ah, Jeff, you asshole. So what goes into that last spot?
I have a question. Are we
Yes.
to switch them to percentages after, since the expected ones were in percentage?
Oh, you'll see in a minute.
Am I saying it right? Okay.
You'll see in a minute. So you're thinking the other way than what we're going to do. So you'll see. Technically, you could actually do what you're saying, but it's not what we normally do. Anybody get this last thing yet?
38.
Yeah, how'd you get that?
You take the total of all the numbers you've done so far, subtracted by the total number of people, which is 500.
Yeah, so does that add up?
Yeah, I thought it was more.
Yeah, it's got to be more. You got the right idea.
48?
Say again?
I
48?
think it's 48.
48. That sounds better. Because these all add up to be, what is that? 324, 52? And so I need 48 to make 500 total. You guys all with me? Don't let that be a problem. You better, the observations better add up to be the total number I talked to, right? Okay. Now, here's the question. Oh shit, Jeff, really? What did I just erase? That was 219, yes. How do I fill this business in? So if I have 500 people, how many would I expect to show up in this category if they followed the general population distribution?
26.4.
How'd you get that?
I took 20% of 132.
There you go. I like it. You guys with me? So it's sort of the opposite of what you were saying, Melody, right? I think that's what you were saying. So you do 20%. So you do 0.2 times 132, and you get 26.4. Okay, let me take that away. I think you guys will just write 26.4 so you can read it. So you do 20% of, wait a minute. Oh, Jeff.
That doesn't work.
I'm silly. Hold on.
Stop.
I'm with you. This is a problem with me just sitting here agreeing with what you're saying. I got 500 people. That was my whole point. I got 500 total people.
20% of
That's
500.
why I was so
There we go.
confused.
There we go. 20% of 500 people. All right, that's better. Because what does the expected have to add up to be at the end?
500.
500, exactly. And there was no way we were going to do that with 26. All right, so what's 20%?
100?
Yeah, 100. I would expect 100 people. Okay. What about this category?
30% of 500.
Good, 30% of 500. For
150.
150, I like it. And then 35% of 500.
175.
175. And then finally, 15% of 500.
75.
75. And thankfully, these all add up to be
500.
500. I like it. So if they did follow the general population, then 20% of the people there should land in this category. Now, this is why a sample being different isn't good enough, because I expect fluctuations in any group, right? Any sample I take, there's going to be fluctuations. They're not going to match it perfect. That's why the sample's got to be so far away from what's expected to be evidence that there really is a difference for the whole area. And then if we find a difference and it's good, it's like lower cholesterol, then we'll go in and do more studies. Is it the water? Is it the exercises they do? Is it, what is it? I'm sorry, go ahead. Does somebody have everybody's good? All right. So now you guys are gonna have to help me. Now you have to do, now notice this. You could do this in your calculator, correct? L1, L2. This would be L1 minus L2 squared. You guys understand what I'm saying? If you wanted to, right? Just have it done, bam, bam, just copy it down. Let's see, is this 964? Is that what this is? No, it's 1,000, hold on. 1,024? Sorry. Is that better? Okay. Yeah, don't hesitate to correct me. I don't know what that one is. Holy shit. It's gonna be 69 squared. I don't know what that is. Are you kidding me? Let's see, 4,900 minus 140, so 4,761. Is it gonna help me?
Yeah, that's right.
Sorry. I think I made up for that first mistake. And that one is just 74 squared. What is that, math boy?
5476.
Damn, I was way off. No, that's not right. Is it? What are you trying to do, Jeff? Did you even think about this right? I think you're probably right. Yeah, you're right. Holy, I can't even get in the calculator correctly. All right, I'm with you. 5476. And now somebody's done this one by now, right? Is anybody not understanding where these numbers are coming from? You can privately chat me if you feel you don't want to say out loud that you don't know where these numbers are coming from. Is there anyone right now that has no idea where some number we've got here has come from? Anybody? Going once. Going twice. So, okay. So what's the last thing here?
729.
I like it. Those look huge. Then we got to, sorry.
If we're doing these in the calculator,
Yes.
L4 would equal L1 will equal L3 divided by L2.
Beautiful. Exactly. So this
Wow.
first one,
I got it right.
this first one's nice, right? You just got to divide by 100. That was easy. The next one, let's see.
174.
What is it?
3174.
3174. Okay. Guess so. And then, sorry. Somebody save me from myself.
31.29.
29? Yeah.
Yes.
And then this thing.
9.72.
Okay, that makes sense. All right, so look at this chi-square value. Holy crap. I thought I changed this. Oh well. I made this and the chi-square is so crazy, but oh well, I forgot to change it. So it's still crazy. 72, 81, 82.46, 6686, 82.99. I lost it.
Yeah, that's what I got.
All right. Even though this is pretty new to us, is that very far away from zero?
Yes.
Yeah, but here's the other part of this. The categories are small, but if the number of categories got larger and larger, now this is where I'm being really stupid right now, because to pull up my chi-square chart, I'm actually going to have to lose everything I've written. Boy, I'm a smart boy. All right, has everybody got this stuff written down? Jeff, you're so smart. Big brains. All right,
Will you also upload this as on the modules?
I will. What do you mean? I'll upload. Wait, I can't. I'm sorry. This is where I'm being really stupid today.
All right, no worries. A screenshot.
Or I'm just continuing to be stupid. Maybe, I don't know. So I'm going to stop sharing, and all of this work's going to go away. Are you guys ready? So I can look at the chi-square. Okay, Nicole's ready. She's like, I don't want to look at that anymore. Okay, it's gone forever. So let me open my chi-square. Jeff, what is going on with you? Why did you close this? I don't know. Where is it? There it is. Okay. So, what's my degrees of freedom?
5.
Yes, so I got, let me see, I need to show some more. There we go. The degrees of freedom is 5. Is it 5?
It's 3, isn't it? It's
3,
4.
that's better.
Oh, sorry.
That's right. The
I got
5,
the other
that was the last one. Yeah, there's 4 categories, right? The 4 categories of cholesterol level minus 1. So our degrees of freedom is 3. Draw you a little Job of the Hut. So I want to go to 3. And then what was alpha, did I say? Somebody looking at their
0.01.
0.01. So here's 0.01. So if I go 3.01, I get 11.345. I don't know, guys. Do we make it? Yeah, that's what counts as humor. Sorry. Yeah, we got way the shit out here, didn't we? What was it? 80 something? 82.99, is that what it was?
Yeah.
How did you get the area as 0.01 again?
Somebody told me that's what it said on the worksheet. So I was crowdsourcing that. So anybody got the worksheet open?
I do.
Did I say 0.01?
Find a group of 500, 101 have a level. I don't see 0.01 now. Is there evidence that this does not match the general pattern at 0.01 LOS?
There it is.
No, got it.
LOS, of course, is little old socks. No, it's level level of significance. Most of my jokes are just for myself, which is fun. The little fish dude, right? So that's where we got here, 101. I kind of like how this is set up because you can kind of imagine it's like this. So these tell me where this tail is going to be for far away.
What do we call that number? What do we call 11.346?
What do you call the z-score that's on like your rejection region? Don't you just call it z? Isn't this just a rejection region? So this is the chi-square score that defines my rejection region. And we just obliterated it, right?
So chi-square is like opposite of z, kind of in the sense of that it goes upwards, like to the right.
Oh, I see what you mean. Yeah, z-score. All right, I will go back and tell you, now that we're a little more used to this chart, I am going to show you one really neat connection between z and chi-square. And by the way, you never square root this thing. That's part of the symbol. If you square root, it's going to go, what am I? I don't even know. So don't square root chi-square. Okay. It's just part of the symbol. It's what it is.
So is the 82.99, is that like chi-squared starred? Is that?
Yes, I love it. Yes, I actually used to call it chi-square starred. I drove people insane, but you get my point. It's just like Z star. So this is the Z, this is like the Z score that defines the rejection region. It's a chi-square. And this is like Z star, but it's a chi-square. Now, similarities quickly fall apart. Look if I had 14 categories. Look what happens to the rejection region. Do you see that? It grows pretty quickly. Yeah. Okay. All right, Jeff. Oh yeah, that's right. I want to show you something kind of cool. What I have to do is remember how this works. I can do that. Can you do that, Jeff? I think so. There it is. Okay, I got it. Yay. All right. By the way, what would the conclusion be here? Did we find evidence that the people have different cholesterol levels than expected?
Yes.
Yes. 0 means they had exactly what we expected. The sample did, right? So if I get further from 0, that means they were not as expected. And these people, I mean, hello, right? So the conclusion would be that these people have very different cholesterol levels than expected. Now, if you look at is a lower cholesterol level better than a higher one, or which way does it work? I'm not asking because I don't know. I'm asking to see if you know. Is it better? Lower is better, exactly. So on this, in the secluded area, if you look back at the worksheet, did more of them have lower cholesterol or higher cholesterol? Here, I'm going to share that sheet again. I'm going to stop sharing this. You guys ready? This is going to go away forever. No? Okay.
There was lower numbers with the higher cholesterol levels, like the observed numbers of the.
So fewer had high, more had low. So, and look at this number. If this was true, if there was a secluded area somewhere and we went in there, we tested the cholesterol levels and we saw what we saw, we got this very different in which direction? In a much better direction. We're like, what the hell are these people doing? Is there, and being Americans, we would hope that there's some special route we can make into a pill that we can pop and not have to worry about shit. But it could just be that they don't have cars, they walk everywhere, they don't eat high fructose corn syrup, they whatever, right? I don't know. They don't have any Burger Kings, or they don't have any hamburgers. Sorry, or kofifi. So let me stop. I'm going to stop sharing. Are you guys ready for that? Somebody got it. Okay, thank you. Hamburgers. I don't think I'll ever live that down. All right, I'm going to stop sharing that. Live that down. I mean, forget it. Let me show you one really cool thing, and then we'll call it a day here. So let me ask. Yeah, I can do it, right? I'm being stupid. Why did I think I had to change this? I can be right here in the same place. Somebody help me out. What is it, Jeff? Shit, I gotta turn this on. Hold on. There we go. In a normal curve, what is the Z-score that has for a 95% interval? What are these two Z-scores here? If I want to make a 95% confidence interval for a normal curve.
1.96.
1.96, I like it. So negative 196 and positive 196, right? All right, now, this is not, I'll tell you what. All right, I'm going to come back. I got an idea. Screw it. I'm not going to do that. Sorry, guys. Sorry. So there's 2.5% here, right? And there's 2.5% here. Are you guys, is that cool? Now, stay with me, stay with me. This is the last thing we're doing today, right? Last thing. I just want to show you something cool. If I folded it right in the middle, can you guys imagine? I'm going to take it and I'm going to fold it on itself. Yes? I'm going to fold it on itself. So like it's going to grow. So right on the fold, it's gotten 0% so far, but then it grows really quickly. So it basically looks like that. You guys are going to have to believe me. Now, listen. This is neat. This is neat. Actually, it wouldn't look like this, but that's okay. If I fold this on itself, can somebody do this for me? What is 1.96 squared? I don't know why I put parentheses, but that's all right.
3.84.
A4
16.
stuff. Right? Is that cool?
How did you get 1.96 so fast? I don't see it in the z-score chart.
Well, because some people have memorized it because it's one of the more often used ones. But you look at 0.05 two tails on the T-chart and go all the way down.
Gotcha.
You can't look up 0.95 in the z-score chart because that's not a confidence interval. Yeah. I really want you guys to understand. So if I fold this on itself, so I have 5%, right? 2.5%. So there's 5% out here. This number times this number is 3.841 basically, and that's exactly what's happening here. So
3.841 is your chi-score?
Yeah, so chi-square, for degrees of freedom of 1, chi-square is just folding the z on itself, squaring all the z scores, making it sort of like an absolute value because then it starts at 0. And then it gets a little weirder as the degrees of freedom go up. It doesn't quite follow that exactly, but there's like a multiplier you can make. But for this first row, if you took a square root, for example, if you took a square root of this, you should see, let me see if I remember this correctly. Yeah, take a square root of this and you get 2.576. Does that look familiar? So one reason they call it chi-square, this is almost too much to throw at you at once, but it's basically like a z-score is a type of thing. What do I want to call it? It's a parameter of a problem. So I can square that and it follows a chi-square distribution. Now there's obviously more to the story because as the degrees of freedom go up, things change very much, obviously. But I at least wanted you to see that connection between the z-score that we're used to working with and this new chi-square. It's really neat. You fold the z-score on itself. It's kind of nifty. Somebody says nope in the chat. I'm not sure what that's about.
The thing you said about the z-score and the chi-score, that went completely over my head.
That's okay. Do you have to understand anything I just said to be able to do anything in this chapter? No, you don't have to. It's just me showing you something kind of neat. You can at least see numbers coming here from the square of numbers we know. That's enough for today, guys. That's enough for today. So tomorrow we'll do some more from chapter 11, and then we'll see, maybe we can start reviewing for the final early.
Can we review for the quiz tomorrow, possibly?
The quiz is happening today, and I guess tomorrow too, but
I mean, just a review, or now, just a quick review of 9 and 10, or you need to go somewhere.
Not really, but I want to remind you here.
If you can just tell me what to look at, I'll look at it.
The best thing to look at would be the practice quiz that I have a solutions video up for, right?
Okay.
Yeah. So the practice quiz, these 2 problems. Wait, those are 2 problems? Yeah, there's 2 problems. And the video. Do you guys, anybody else realize this is up there for you? Solutions video. And the answers are right here too. You can download, just if you just want to see the answers, you just download that right there and don't want to listen to me. You're like, good Lord. All right, listen to this guy. Oh god, just give me the freaking answers. You can just click right here and get the answers, or you can watch the video. Okay, and you can change. You can make me go faster if you're like, good lord, can this guy just get to the point? You can actually make me go faster. It's crazy. But I mean, you know, I'll entertain questions if anybody needs to hang out afterwards. If you have questions, let me know. Otherwise, you're free to run away from the Terminator. Sometimes I forget about this and I go in stores and people are like, are you okay? I'm fine. The time is now.
Could I ask you a quick question about number 76, 4 point, what was it? 4.
Oh yeah, you were talking about the 4-2, right?
Yeah, I'm just working through all of my corrections, and for the homework, you crossed it out, and then I was confused why you crossed it out, and then you asked for the standard deviation. So I just wanted to make sure I got
Yeah. So on the homework sheet, I said for this problem, I wanted you to also find the standard deviation.
Mm-hmm. So I think I found that, but the part that you crossed out, is that incorrect?
I don't know. I have to look yours up. Hold on. Let me answer a question in chat real quick. I'll never ask you. So there's a question in chat. I will never ask you to find the p-value for a t-score problem because you can't. I have not given you enough to be able to do it. The t-score chart is not detailed enough to find the p-value for a t-score. Technology could do it, and I don't care about that. What am I looking up? Oh yeah, you're section 4.2. All right, let's see. No, I'm really sorry. Who am I talking to right now? Was it Melody or Katrina or
Patrina.
All right. There you are. So number, where'd it go? There. No, wait. Which number again? 76? There it is. Oh, all right. So it looks like I crossed through the whole thing, but it was just an arrow going up to the probability. Yeah, I wasn't sure. Oh, you added, all right, so let's start with part D first. Well, that's actually the only thing you got wrong, really. Where are the probabilities in the chart?
What do you mean, the probabilities in the?
Where are the probabilities in the chart, in the X P of X chart? Where are the probabilities?
Oh, I think I just.
Yeah, you added the stuff in the third column, not the second. Second column of the probabilities.
Yep, and that
more than
adds
one.
up to 1.
Sorry?
That adds up to 1.
Sure, but look at part D.
Yep.
They're asking you what's more likely, but
I looked at the third column instead of adding up the.
You're saying 120% chance. Yeah, right?
Okay, got that.
Okay. And then the only other thing that was wrong, so that's just a big arrow. That's not crossing through everything. Everything else was fine.
Okay, that makes more sense. Because I was like, I did it twice and I'm like, wait, this is still correct.
And then I just added onto the homework sheet, I said, calculate standard deviation. So you got to make that other column x squared p of x.
Yes.
Make that, yeah. So you
And
can
then
make
x squared p of x. Is it, so the x minus mu squared times p of x is the exact same formula as.
Well, it's more work, and yes, it's the same.
X squared p of x minus mu squared.
Yes, they accomplish the same thing. Yeah, they are the exact same formula, even though they don't look like it.
For that one, I just plugged it all into the calculator. Do you want me to like draw it out?
What? Yeah, I have to see that fourth column.
Okay, got it. That was it for that one. Thank you.
Cool.
Hey, buddy.
Yep.
I just wanted to finish going through the midterm with you when everyone else was done with their questions. So I can wait patiently, or we can dive right in.
Just got to change your name there. There we go.
Oh, thanks.
All right. So what are we looking at?
We were looking at page 2, where I start with 6, which we've gone through, and now we're at 5.
All right, here we go. Well,